back, everybody, and welcome to Section 2. So we've talked about metamorphism and what it is, we know where it happens, but what does a metamorphic rock actually look like? Let's find out. So what do metamorphic rocks actually look like? Let's start with the pictures here. One of these is an igneous rock and the other one is metamorphic. How can you tell? Well, this is going to be the igneous rock up on top. If we look at it, there's no real pattern, no particular area looks different from any other, it's just kind of a mix of all these different crystals. On the other hand, the metamorphic rock, we do see a pattern. We have these sort of stripes, these black lines all going in the same direction across the rock. This is called foliation. It's a result of the pressure that rocks experience during metamorphism. And this foliation gives them this sort of layered or banded appearance. Something else you might see in metamorphic rocks are veins. So it's going to be these little white patches, thin and narrow. So this rock was cracked either due to exposure to the elements or due to pressure. And as it's buried underground and goes through the metamorphic process, those cracks are filled with hot, mineral-rich fluids. Well, those fluids leave minerals behind. In this case, it looks like quartz. And these become veins. It gives the rock this sort of veined appearance. So foliation is kind of a big category for all sorts of different metamorphic textures. And veins, it's sort of like texture, but it's kind of in its own category. It's something that happens secondary to the rock, depending on the environment that it's in. What if we want to talk about just the different types of metamorphic textures specifically? Well, we're going to talk about 4 types here. We have slaty cleavage, schistosity, mineral banding, and magmatic texture. So our first texture is slaty cleavage. This is one particular type of foliation, and this is what it looks like. When you look at all these different rocks, you can see that it's formed in these thin parallel layers, right? And these layers don't form randomly. They form in a direction that is perpendicular to the maximum stress. What does this mean? Well, let's say that we took a patch of unaltered, unmetamorphosed rock. We expose it to high heat and high pressure, squeezing it from the sides. Well, because the pressure is coming in from this direction, we know that the slaty cleavage will end up looking like this in the rock. It forms perpendicular to the direction of maximum stress or maximum pressure. This is an example of low-grade metamorphism. It is seen in things like slate, of course, and phyllite, which is sort of like a slate that has been cooked a little bit more. So if you actually were out walking around and you came across slate in an outcrop, it might look like this, right? Have these big, square-ish chunks of rock full of these little horizontal layers. What do those layers tell you? It tells you that the direction of maximum stress would have been going this way. The rock was squeezed like this, and now the layers are in the perpendicular direction. So why talk about cleavage? Why is this important? Well, it's important because it tells you something about what originally happened to the rock. So we can look at our first example here. We have these horizontal layers of sedimentary rocks, and these sedimentary beds are in the same direction as the slaty cleavage. Why? Because the slaty cleavage is under the most pressure from the top and bottom. Lower grade metamorphism. So later on, if you came across something that looked like this, and you saw that this cleavage is parallel to the layering of the sedimentary rocks in that area, you could work backwards and see, well, there's really not that much pressure, there's not that much activity going on. Now, on the other hand, you could see something that looks like this in an outcrop. So you have these sedimentary layers, which are going one way, and then you have vertical cleavage in the rock. That's what these vertical lines are here. Well, it tells you that the original setting would have looked something like what's here in the diagram. It tells you there was a ton of compression coming in horizontally, something that might have happened as a result of the collision of tectonic plates, a huge amount of horizontal stress. And that horizontal stress comes in and takes sedimentary layers that were originally horizontal and folds them up, and it leaves behind this sort of vertical cleavage. So you could come back later, see the cleavage, see the relationship between that cleavage and the sedimentary beds, and it would tell you something about the history of that area. Some other fun facts about slate: it is commonly used in pool tables. It's extremely smooth, or it can be, and very, very heavy, sturdy. It is also used for roofing. So we might go through an example one more time. This is what our original sedimentary beds look like. We know that sediments are deposited horizontally in these horizontal layers. This is our starting point here. And it goes through some sort of horizontal compression, maybe due to continents colliding in plate tectonics. Now, the shale, mud rock, becomes slate, the metamorphic rock. Sandstone becomes quartzite, which is a metamorphic rock. The layers get folded up, and the cleavage reveals to you that this was the direction of maximum stress during whatever tectonic event would have deformed the rocks. So whenever you see something that looks like this in the field, you work backwards, you figure out what happened in this stage, and you might be able to recreate what the rocks looked like originally. The next texture is called schistosity, right? Like schist, the rock. And it makes a rock look like this. It's extremely shiny. You have this layering due to the parallel arrangement of flat, platy mineral grains. Now, you might get other things present in these. A lot of times with schist, you'll have garnets that give it away, tell you what kind of rock it is, or these things called starlites, these little twinned minerals. This is going to be an example of intermediate grade metamorphism. So if we took something that is a slate and we cooked it even further, buried it deeper in the ground, it would go from slate to something called phyllite, and finally to schist once it got cooked enough. Now, even though schist was very shiny in that last slide, if you looked at an outcrop, it would look a little bit more like this. Notice that you can still see this sort of layering to the rock. So one other kind of foliation in metamorphic rocks is called banding. You notice that we have these alternating layers of light and dark minerals. This represents higher grade metamorphism, and the rock we're looking at here, the most common example of this, is in something called a gneiss. If you come across gneiss in the field, what would it look like? Well, maybe something like this. Notice that you can still see these sort of alternating layers of light and dark minerals, or something like this. Notice the alternating layers of light and dark minerals. And the final texture we're going to talk about is called magmatic texture. And before we do this, the first thing you should know is that the first number in the access code is 6. First digit is the number 6. So a magmatic texture is something that's sort of halfway between igneous and metamorphic. You have something that has been exposed to such heat and such pressure that it sort of starts to melt a little bit, but not all the way. And when it cools, it looks something like this. This is called a magmatite here. So in this section, we talked about metamorphic textures. If you had an igneous rock in one hand and a metamorphic rock in the other, how could you tell the difference? Well, you would look at things like foliation. Maybe one of them has a little bit of banding to it, and that would help you to tell the difference. In the next section, we are going to talk about specific metamorphic rocks. So we've talked about things like slate and phyllite and schist and gneiss, but what exactly are these? What are they made of? What do they mean? That's what we'll cover next.